Right, so in this video I'm going to look at proof by induction, and I'm going to do it for series or a summation. So I'm going to do this particular example here where I've got the sum of r squared, where r goes from 1 up to n. I'm going to prove that that's equal to n over 6 times n plus 1 times 2n plus 1, for n being an element of n. In other words, n is a natural number, 1, 2, 3, 4, 5, 6, and so on. So I'm going to do this in 4 steps, and the first step is to show that the proposition is true for n is equal to 1. Show that this is true for n is equal to 1. So in other words, look at the left hand side here. If I put 1 in instead of r here, I get 1 squared, which is just 1. So the left hand side will just be 1. On the right hand side, if I put 1 in here, here, and here, I get 1 over 6, 1 plus 1, 2 times 1 plus 1, which is 1/6, 2 times 3 is 6, 1/6 of 6 is 1. So on the right hand side I get 1 as well. So the proposition is true for n is equal to 1. The left hand side is equal to the right hand side when you substitute 1 into your equation. So that's step 1. Now step 2 then is an assumption. I'm going to make an assumption in this case that the proposition is true for n is equal to some number called k. So in other words, 1 plus 4 plus 9 plus 16, in other words that's 1 squared plus 2 squared plus 3 squared plus 4 squared up to k squared, that's this here, is true for some number k equal to k over 6, k plus 1 times 2k plus 1. So I'm going to assume that it's true for this number k here. So this is true. Now step 3 then is going to be to prove that it's true for the next number up from k, in other words k plus 1. So I'm going to prove that the proposition is true for n is equal to k plus 1. In other words, I'm going to have 1 plus 4 plus 9 plus and so on up to k squared plus another k plus 1 squared. So this is the k plus, this is up as far as k up as far as k, and this is up as far as k plus 1. I'm going to square it. Now on the right hand side I'm going to end up with k plus 1 over 6, k plus 1 plus 1, and 2 times k plus 1 plus 1. So this is the right hand side where I just substituted in k plus 1 here, here, and here. Okay, so I've got to prove that the left hand side is equal to the right hand side here. Now if you look at the left hand side here, you've got from here to here is just the left hand side of our assumption. So in other words, this part here I can just substitute this here I can substitute this part here for it. So in other words, up as far as here, from 1 up to k squared, I can just write this. So that's what I'm going to do on the left hand side here. So in other words, k over 6 times k plus 1 times 2k plus 1, that's up as far as here. Then I've got to write in the k plus 1 squared, so that's my left hand side written a different way. On the right hand side I'm just going to tidy that up, so I've got k plus 1 over 6, k plus 1 plus 1 is just k plus 2, and here I've got 2k plus 2 when I multiply out this bracket, 2k plus 2 plus another 1, that's 2k plus 3. So okay, this is what I've got to prove here. I've got to prove that this is equal to this. So I'm going to look at the left hand side and I'm going to try and turn it into the right hand side here. So let's look at the left hand side here and see what we can do with it. Well, first thing I'm going to do is look and see that I've got a 6 on the right hand side, I've got a 6 on the bottom here on the left hand side, I've got a k plus 1 on the top, a k plus 1 on the top, so I've got k plus 1 over 6 on the left hand side here and on the right hand side. The rest doesn't really look similar, so what I'm going to end up having to do probably at some stage is just multiply out all of this lot and factorize probably and try and end up with this here. So let's see if we can do that. Well, I'm going to take out this k plus 1 because there's a k plus 1 in this term and there's a k plus 1 in this term here. So I'm going to factorize the left hand side. So I'm going to take out a k plus 1 and inside here I should end up with k over 6 times 2k plus 1, and here I'll just end up with a k plus 1. So that's my left hand side there. In other words, k plus 1 times all of this will give me this here. K times 1 times k plus 1 will give me k plus 1 squared. On the right hand side, nothing changes. I'm not doing anything with the right hand side. So I'll just write that down again. Okay, so now on the left hand side here, what I'm going to do is multiply out this bracket here. Really, if you look at this part here, that's k times 2k plus 1 over 6. In other words, what I could do is just rewrite that a different way. That's 2k plus 1 here, 2k plus 1. I could just write it like this, 2k plus 1, and I've got a 6 on the bottom here. So that's exactly the same as what I had a few minutes ago. So in other words, I've got I'm going to add these two fractions. I've got this fraction plus this fraction here, so that's all I'm going to do. So I've got a k plus 1 here. Over here I've got lowest common multiple, rather, 6. So 6 into 6 is 1. 1 times the numerator there is just k times 2k plus 1. 1 into 6 is 6 times. 6 times k plus 1 is 6 times k plus 1. So all I've done is added those two fractions there. And again, on the right hand side, I'm not going to do anything. Okay, so that's we're just dealing with the left hand side here, so let's continue that on. So I've got a k plus 1 here. Over here I'm going to multiply this out on the top, so I end up with 2k squared plus k plus 6k plus 6, and then 6 on the bottom here. Right hand side, exactly the same again. Okay, so let's see, I'm just going to add those two then in the middle here, the k and the 6k, so I end up with k plus 1, 2k squared plus 7k plus 6, and that's all over 6. The right hand side, same again, 2k plus 3. Okay, so now I'm going to factorize this here on the top, and hopefully that'll give me something like this. Let's just have a look at that. Let's see, k plus 1. Now factorize the top, and I've got a 6 on the bottom, and here I've got a k plus 1 over 6, k plus 2, 2k plus 3. Now let's see, 2k squared is just 2k times k. I've got a 6 here. Now let's see, 2 times 3 will give me 6 anyway. So if I look at the right hand side, I need a 2k plus 3. So let's just put that in there and see, does that work? And I've got a k plus 2 here. Let's see, does that work? Well, 2k times k will give me 2k squared. Plus 3 times plus 2 will give me the plus 6. And then 3k plus 4k will give me 7k. So this works. These are the factors of this quadratic up here. So that's fine. So if you look at that, I'm multiplying by k plus 1, so I can just, it's k plus 1 over 1 times this fraction here. So it's just simply, I can write it like that. It's just k plus 1 over 6 times k plus 2 times 2k plus 3, and that's equal to k plus 1 over 6 times k plus 2, 2k plus 3. So what I've done is I've shown that the left hand side is equal to the right hand side. So what I can write then is, therefore, the proposition is true for n is equal to k plus 1, given that it is true for n is equal to k. Remember, we made an assumption that it was true for n is equal to k. If it's true for some number k, then it is true for k plus 1. Now, that's the main bulk of the proof. We're just going to make a statement at the end here. So this is, we're going to call this step 4. So we know that the proposition is true for n is equal to 1. If the proposition is true for n is equal to k, then it will be true for n is equal to k plus 1. Therefore, by induction, it is true for all n an element of n. So in other words, we're just making the statement here that we've proven it really. The proposition is true for n is equal to 1. We proved that in step 1. If the proposition is true for n is equal to k, then it will be true for n is equal to k plus 1. So in other words, say n was 1, then we've proven that it must be true for 2. Because if n is equal to k, it'll be true for the next number up, which is k plus 1. So if it's true for 1, it'll be true for 1 plus 1, which is 2. If it's true for 2, it'll be true for 3. If it's true for 3, it'll be true for 4, and so on. Therefore, by induction, it's true for all n is an element of n. So that's the first proof by induction, and it's a proof for a series or a summation.